I find that people get confused a bit about the asymmetry of the general chain rule, that you can basically choose to walk in any direction you want, because the chain rule is, symmetric. Yes, that's generally true, but when it comes to modeling, now we are choosing a specific direction. And as I said last time, the flow of direction is generally from hidden variables to observables. In other words, causation. So, figuring out what models are going to best describe our data is itself a hidden variable, right? I mean, causality is something that we don't just directly observe in most of the problems that we're talking about. DNA is so small we can't directly see it. Basically, we propose models, we propose causal models, and we just test to see which ones probabilistically best fit the data, right? Maximize the likelihood of the observations in the classic form. Question?
I was wondering what you might say about independence and correlation. Kind of came up in discussion. So right now, I think of independence as a modeling decision, and also a mathematical property was correlation as you observe statistically.
Sure. So a couple crucial, hopefully obvious points. When we draw structures like these information graphs and we don't draw an edge between two variables, that doesn't necessarily mean they're not correlated. They could be connected through some other variable, so they're conditionally independent given that variable, but the fact that there's a connection through another variable, they could still be correlated in our data, right? So I definitely agree that correlation should be thought of as something that you can observe, and mathematically, we can formalize that by simply saying, I define a new observable variable computed in the following way from my source observables. And since there's now zero uncertainty about the value of that new variable, therefore, it's an observable by definition, right? So I can, for a correlation coefficient, I can write down that calculation, and the resulting correlation coefficient would itself be an observable by that definition, okay? So you're absolutely right about that. And we can then use it to try to make inferences about what the information graph structure might be, et cetera, et cetera. But basically, what I'm proposing to you is think about modeling as a search for, causal theories of your data, right? And you propose different possible causal models, you test them on the data. Other questions? I'm not sure did I answer your question?
So what would you say about independence? Because I think of right now it's just, it's a modeling decision. So in one model they're independent, in another.
Sure, absolutely. We can propose different, that's what we just did in this problem. We said, in one case, we said that the observations would actually be, conditionally independent given the population allele frequency, right? Because they don't connect until you get all the way back to the top of to theta, right? And in the match model, by contrast, we said they're not conditionally independent given theta because they're connected by kappa, right? So absolutely, proposing different models is fundamentally about saying what matters versus what doesn't matter. Translation, what matters versus what doesn't matter is what is the conditional independence structure of the data, of the problem, okay? So I totally agree with what you just said, and I hope that what I just said helpfully amplified on that. Other things that people are wondering on that? Okay, well, just to try to